The sun just did something terrifying. A vast hole ripped across its surface, bleeding a river of plasma straight toward Earth. And at that exact moment, our interstellar visitor comet 3I Atlas vanished. No telescope could find it. The sky swallowed it whole. If that sentence makes your pulse jump a little, good. Because this is not fiction, it's data. And data has teeth. If this has you on edge, don't just watch, act. Hit like, smash, subscribe, stay locked in as this unfolds. Drop a comment. Where are you watching from, and do you believe we're getting the whole truth? Share this on X, Facebook, Reddit, your group chats. Every share fuels the hunt. You're why we chase these stories. Thank you. October of 2025 arrived with a cosmic alarm bell most people never heard. Scientists monitoring the sun saw something they did not like. A trans-equatorial coronal hole opening across the solar surface. A wound spanning both hemispheres, gaping like the skin of a ruptured star. Through that wound poured the solar wind, an invisible hurricane of charged particles screaming into space at 700 kilometers per second. Imagine a hurricane where every particle of air moves faster than any bullet humanity has ever built. The stream of protons and electrons tore through the void, carrying magnetic fields like barbed wire wrapped in fire. Earth, as usual, sat directly in the path. At first it looked routine. Space weather happens. Satellites endure. Auroras paint the poles. But this time the magnetic alignment was perfect. Almost suspiciously perfect. The polarity of the solar wind matched Earth's own field so precisely that the planet's magnetic shield opened like a door. Energy flooded in, coupling the breath of the sun with the skin of the world. Power grid operators received alerts. Satellite controllers braced for glitches. Pilots reported radio static at high latitudes. And somewhere north, photographers packed their cameras, chasing skies that would glow like spilled paint. Then something else happened. 3I Atlas, only the second confirmed interstellar comet ever observed, disappeared behind the Sunday. One moment it was there, a faint smear of alien ice crossing the inner solar system on an orbit that came from no known star. The next it was gone, swallowed by glare. Timing can be cruel. Earth's magnetic field was being hammered by the fastest solar wind in months. At the exact instant, our lone visitor from another world slipped behind the star, delivering that assault. Astronomers pride themselves on caution. They know coincidence is seductive. They repeat the mantra, correlation is not causation. Still, some glances lingered longer than they should have on overlapping timelines. And then, the ground shook. Seismometers from Asia to South America recorded multiple magnitude 7 earthquakes within hours of the solar storm's arrival. It was enough to make even the most skeptical researcher pause before blaming coincidence again. Of course, geology lectures are firm on this point. Tectonic plates don't care about solar wind. The crust grinds and breaks under internal strain, not cosmic magnetism. The mainstream view is unmoved, but on the scientific fringe, quiet conversations began. Could ionospheric coupling, tiny changes in Earth's rotation rate, maybe shifts in magnetic stress tip? A fault that was already ready to slip, unlikely but not impossible. Meanwhile, the missing comet haunted everyone. 3I Atlas wasn't just any comet. It was a messenger from beyond the sun's kingdom, a fragment of some alien nursery, a sample of chemistry untouched by our star. When it vanished, we lost not just data, but contact with something older than humanity itself. Its disappearance raised questions no one could yet answer. Would it re-emerge unchanged, a survivor of the sun's furnace? Or would we see only debris, dust, or nothing at all? Could the solar wind have stripped it bare, shattered it, or fused it into something unrecognizable? Astronomers peered into the glare, searching for a glint of salvation. None came. For now, the sky was blank. The silence was unsettling, the timing uncanny, the sun bleeding plasma, the earth trembling, the comet gone. Coincidence, said the scientists. Connection, whispered everyone else. And somewhere between those two words, the gap between what we know and what we fear, the story of Atlas began. The story of 3I Atlas begins, like so many cosmic tales do, with patience, Night after night, robotic eyes swept the sky, searching for motion among the stillness. Somewhere in that endless mosaic of starlight, a faint smudge shifted position, and the machines noticed. It came from the Atlas Survey, short for Asteroid Terrestrial Impact Last Alert System, a network of automated telescopes built to watch for killers, not wonders. They were meant to find the rocks that might hit us. Instead, they found a traveller that would never stay. The data looked strange from the start. The object moved too fast, its orbit too wide, its path shaped not like a loop, but a sling. When astronomers ran the numbers, the result made even seasoned professionals whisper. The eccentricity was greater than a hyperbolic orbit. Translation: this thing wasn't from here. Interstellar. That single word changed everything. In a universe of uncounted comets, only 2 before had carried that label. The first Oumuamua back in 2017, a cigar-shaped mystery that spun through the inner solar system and left physicists arguing for years. The second Borisov in 2019, a more ordinary visitor made of dust and ice that reassured us the cosmos still followed familiar rules. And then came the third, Atlas, faster, fainter, and far more enigmatic. The astronomy community moved instantly. Telescope time, normally a bureaucratic battlefield, opened overnight. Observatories from Hawaii to Chile pointed glass and mirrors at the streak of light diving toward the Sunday. Spectrographs broke its glow into colours, each wavelength a fingerprint revealing chemistry written in photon ink. Was its ice the same mixture that built our own comets, water, carbon dioxide, carbon monoxide, and traces of organic molecules? Or would it show alien ratios, chemistry forged around a star with a different light? The first results were confusing. Atlas brightened unpredictably. Comets are supposed to follow neat equations. As they approach the sun, heat sublimates, the ice gas escapes, and the comet brightens along a smooth curve. Atlas refused to cooperate. Its light curve jumped, flattened, and then surged again like a heart monitor with arrhythmia. Something was happening inside it. Either the surface cracking open in sudden jets or pieces breaking away in silence. Astronomers argued gently in academic papers and violently in private chat threads. Some claimed the nucleus was unusually dense, more rock than ice. Others suggested the opposite, a fragile snowball riddled with voids that released gas in chaotic bursts. The truth was buried inside a lump of frozen alien material, millions of kilometers away, unreachable, unrepeatable. Every new data point deepened the mystery. The comet's trajectory wobbled, slightly, small deviations from perfect gravity. That happens when jets of gas push unevenly against the nucleus, creating non-gravitational acceleration. But Atlas's shifts were stronger than expected, as if invisible hands kept nudging it off course. Each refinement of its orbit changed predictions of when it would pass behind the Sunday. The error bars stretched wider, the certainty evaporated. Scientists don't like uncertainty. They live on it, but they never like it. Some observers thought they saw elongation in the coma, the faint glow surrounding the nucleus. Not a perfect sphere of dust, but a stretched, uneven plume. It could mean nothing, or it could mean the comet was already splitting apart. And if it was fragmenting before it disappeared, then what would emerge might not be a comet at all, but a cloud of ghosts. This is where science begins to resemble grief. You build models, you feed in data, you project outcomes. You hope the universe will behave long enough for you to understand it, and then it doesn't. Behind the sun, Atlas entered the blind zone, an astronomical purgatory where no telescope can follow. The light is too bright, the geometry too cruel. For days, maybe weeks, the comet would exist in a place no human eye could reach, and during that absence anything could happen. It could disintegrate, completely vaporized by solar heat. It could split into shards that drift apart like cosmic ashes, or against the odds it could survive transformed but intact, emerging as a scarred survivor from the solar inferno. No one could know. And yet hope persisted. Models kept running. If the nucleus was large and rocky, it would endure. If small and icy, it would perish. The difference between those scenarios was a few hundred meters in diameter, an invisible detail deciding the fate of something older than our species. Meanwhile, the internet buzzed. Alien probe trended again because of course it did. Humans are pattern machines, and when faced with data that defies explanation, we default to mythology wrapped in pseudoscience. A rock from another star becomes a message. A disappearance becomes a plot. Astronomers rolled their eyes and kept working. They were looking for photons, not purpose, but even they felt the weight of waiting. Somewhere behind that blinding curtain of plasma and magnetism, an object from another sun was either dying or enduring, and humanity could do nothing but wait for the light to return. The phrase whispered across observatories became almost poetic, invisible interstellar traveller. That traveller now drifts unseen, its fate unwritten. And if it comes back changed, brighter, darker, or shattered, we will face the same question again. Did the sun merely illuminate it, or did it consume it? The sun is not kind. We like to imagine it as benevolent light, gold on leaves, warmth on skin. But up close, the sun is chaos incarnate, a roaring sphere of plasma where temperature and magnetism wage endless war. And when that war spills outward, everything nearby feels it. The event that swallowed 3I Atlas began with one of those ruptures. A coronal hole spanning the sun's equator magnetic fields twisted open like torn seams. Through those gaps poured streams of charged particles moving faster than imagination, allows 700 kilometers per second, almost twice the speed of an ordinary solar wind. To us on Earth, that translates to geomagnetic storms, auroras, the occasional radio blackout. But to a comet, it is something else entirely. It is impact without collision. Comets have no magnetic shields, no planetary armor. They are fragile snowballs drifting through violence. When a solar wind like this one hits a comet's coma, the halo of gas and dust that boils off its surface. The result is an invisible war between electricity and ice. The gas becomes ionized, each molecule losing electrons to the flood of solar radiation. Magnetic field lines embedded in the solar wind drape around the comet, forming a long tail of plasma, millions of kilometers long. That tail is not static. It writhes and shreds as the magnetic field fluctuates, sometimes snapping off entirely and reforming, a disconnection event that makes even seasoned astronomers mutter quietly in awe. Now imagine that happening not to an ordinary comet but to a visitor from another star system, an object never designed for the ferocity of our Sunday. When coronal winds that fast strike interstellar material that fragile, the interaction becomes unpredictable. Turbulence in the magnetic field can rip away the coma. Solar radiation can ignite jets, spin the nucleus, tear it apart. The sun, in effect, becomes an executioner. History offers grim examples. Comet Eisen, discovered in 2012 and hyped as the comet of the century, disintegrated completely as it approached perihelion a year later. Cameras on solar-watching spacecraft recorded its final moments, a bright streak entering the furnace and nothing coming out. Others, like Comet Lovejoy, somehow survived, emerging shredded but alive. Predicting which path Atlas would take was like guessing whether an ember will fade or flare in a storm. Inside the scientific community, two camps formed. The conservative majority said it was coincidence. Atlas happened to disappear during a solar wind event. The smaller, louder minority whispered that the timing might not be random. They pointed to the so-called electric comet model, an alternative theory proposing that comets can accumulate large electrical charges as they move through the solar wind. Under certain conditions, those charges could discharge explosively, fragmenting the nucleus from within. Mainstream physics rolls its eyes at that model. It violates nothing in known equations, but it requires assumptions no one can yet test. Still, the idea refuses to die. When Atlas vanished during the strongest solar wind in months, the electric comet believers smelled vindication. The truth is probably duller and stranger at once. Comets are fragile assemblages of dust and ice, each one unique. Some are dense as rock, others are fluffy as aerogel, barely held together by gravity, weaker than a human handshake. A slight spin, an uneven jet, a heat wave penetrating a pocket of gas, and the whole structure can come apart silently, atom by atom. If Atlas was already cracked before it vanished, the solar wind could have been the final insult. If it was porous, heat would have sunk deep, cooking it from the inside out. If it was dense, it might have survived, but lost its outer layers, leaving a darkened core wrapped in silence. Each scenario ends the same way for now: invisibility. And that invisibility gnaws at us. Behind the sun, Atlas drifted through plasma dense enough to strip atmospheres. For weeks, we had no data, no light, no confirmation that it even still existed. In a scientific age, that kind of blindness feels almost personal. The sun, of course, offered no comment. It just kept burning indifferent, its magnetic wounds widening and healing in endless rhythm. Somewhere behind that brightness, something alien was being tested, and we were left with only probability and hope. If Atlas emerges intact, science wins another puzzle piece. If it disintegrates, we gain only questions, and questions are heavier than debris. Maybe the sun didn't destroy it. Maybe it transformed it, melted it into a new shape that carries the memory of two star systems, the one it came from and the one that tried to erase it. Either way, what happens next will tell us something important about survival in a violent universe, because if a frozen relic from another star cannot endure the breath of our sun, what chance do we have when the same wind eventually turns on us? Waiting is not a science, but astronomers have turned it into one. The moment 3i Atlas slipped behind the sun, the countdown began. Telescopes went idle, software queued recovery sequences, and the world's best minds settled into the most excruciating phase of any cosmic mystery: the silence between data points. They called it the conjunction gap, that period when geometry itself conspires against us. The sun sits directly between Earth and the target, its brilliance drowning every photon. Even the most sensitive instruments must look away. It's a forced blindness, like covering your eyes during a solar eclipse and trusting that when you open them again, the universe will still be there. For now, 3i Atlas exists only in prediction. Orbital models trace where it should be, not where it is, and those models carry uncertainty, the small errors that grow with every day of invisibility, until the line on the graph becomes a guess rather than a path. Still, they prepare. Space-based observatories like SOHO and the twin stereocraft stand ready, each equipped with coronagraphs that block the sun's glare by creating artificial eclipses. If Atlas survives, these instruments will see it first, a faint ghost crawling out of the light. The Parker Solar Probe, humanity's closest emissary to the star, cuts through the region where Atlas now hides. Its instruments measure plasma density, magnetic turbulence, solar wind velocity. If the comet crosses Parker's field of view even for an instant, the data might hold a whisper of its passing. But the odds are small. Space is wide, the comet tiny, and the sun mercilessly bright. So they wait. Astronomers plan the recovery campaign like generals before battle. Which telescope will point first? Which filters to use? What exposure times to risk? Amateur observers across the globe join in small backyard telescopes standing shoulder to shoulder with billion-dollar instruments. The first glimpse, if it comes, could come from anyone. Best-case scenario, the comet reappears fainter than before but whole, its coma glowing softly with sublimating ice. The tail stretches behind it, proof that the nucleus survived the ordeal. Spectrographs will dissect the light, searching for familiar lines: water vapor, carbon monoxide, cyanogen, the fingerprints of life's raw ingredients. Worst case, nothing. No light, no movement, no trace. The coordinates where Atlas should be remain empty, the sky pretending nothing ever passed that way. Between those extremes lie infinite maybes. It could return as a swarm of fragments, a necklace of icy pearls tracing the same orbit, each one a remnant of what was once a single body. It could come back dormant, its surface sealed under a crust of baked dust, no longer venting gas, no longer glowing, just a dark stone tumbling quietly through sunlight. And if it returns that way, the question becomes philosophical. If the nucleus remains but its soul, the outgassing, the tail, the radiance is gone, is it still a comet? Or is it something else now, something unnamed? Astronomers pretend not to care about such semantics, but in the long nights between observations they do, because every comet carries meaning. These icy relics are time capsules storing the chemistry of creation. Losing one feels like losing a page from the universe's autobiography. The vigil takes on a ritual rhythm. Each day, new predictions refine the probable date of reappearance. Each night, telescopes idle, listening for silence. The cosmos doesn't hurry, and humans, despite our equations and supercomputers, remain its impatient students. Weeks pass. The sun's glare begins to thin as geometry shifts. Soon, observation will be possible again, and somewhere perhaps already moving through that bright emptiness, Atlas drifts broken or whole, dead or alive. The first photons will tell the truth. They will cross 100 million kilometers, touch a mirror, strike a sensor, and resurrect a story that for now exists only in memory. Until that moment, science becomes faith, the quiet conviction that light once lost always finds its way home. Coincidence is science's least favorite word. It explains everything and nothing. And in October of 2025, the coincidences came too fast for comfort. A solar storm powerful enough to twist magnetic fields across half the sun's surface. An interstellar comet vanishing at the same moment. Earth trembling under multiple magnitude 7 earthquakes within hours of the impact of that solar wind. For geophysicists, the explanation was simple coincidence. For everyone else, it was a story. Humans are pattern hunters. It's what saved us on the savannah, seeing shapes in tall grass before the leopard moved. The same instinct that once saved our ancestors now drives our news cycles. We connect dots even when they belong to different pages. So when the sun flared, the ground shook, and a comet disappeared, people demanded meaning. Surely the universe wasn't just rolling dice. Mainstream science drew its boundary quickly. Earthquakes come from plate tectonics, not plasma storms. The crust of our planet moves because rock fractures under pressure accumulated over years, not because magnetic waves brushed the atmosphere. The solar wind stops far above the surface, caught by the magnetosphere, its fury diffused long before reaching the ground. But not everyone is satisfied by equations. At the margins of respectability, researchers whispered alternate possibilities. Maybe ionospheric disturbances alter the electrical charge of fault zones. Maybe the momentum transfer from solar wind modifies Earth's rotation by microseconds, just enough to nudge a fault that was already primed to fail. Maybe. Each maybe was a seed, and online communities of fertile soil. By the time the sun had quieted, the internet was loud again. Charts appeared, showing solar activity spikes and earthquake clusters. Arrows connected events across continents. Correlation lines ran like spider webs. None of it proved anything, but proof is rarely the goal. People want narrative, not null results. And narratives multiply. Some claimed Atlas carried something data matter life and the sun had destroyed it deliberately, a cosmic quarantine. Others decided the opposite, that the comet was a messenger and our star overreacted. Theories about hidden civilizations, alien technology, and plasma weapons bloomed overnight. Astronomers rolled their eyes. Scientists measured magnetism and muttered about statistics. But beneath the sarcasm, even they felt the pulse of unease, because the coincidences, while meaningless on paper, felt uncanny in the bones. The human brain is a pattern machine. It would rather believe in purpose than accept randomness. When you tell people that solar storms and tectonic strain have nothing to do with each other, they nod politely and then go online to find someone who says otherwise. There's comfort in conspiracy. It gives chaos an author. History repeats this pattern like clockwork. After every eclipse, earthquake, or comet, prophets rise and predictions follow. They promise connection. They promise meaning, even when the universe offers none. Still, not all speculation is madness. Science itself begins with suspicion, with the feeling that something doesn't fit. Those who explored faint statistical correlations between solar activity and seismic events were not heretics. They were simply curious. Most will find nothing. A few might find anomalies worth explaining. And that's the paradox. The same pattern-seeking instinct that fuels superstition also drives discovery. The difference is discipline. One tests, the other believes. In the quiet after the headlines faded, scientists returned to their models, filtering noise from signal, replotting data, tightening error bars. They know patience beats passion in the long run, but they also know emotion drives the crowd. The crowd doesn't wait for peer review, it scrolls. Meanwhile, the comet remained hidden, silent behind the Sunday, and as weeks passed, the absence became its own kind of evidence. Some said agencies were hiding the truth that images from space probes had been censored. The logic was circular. The absence of data proved suppression of data. It's hard to argue with faith disguised as skepticism. In the end, the conspiracy wasn't about aliens or the sun or seismic coupling. It was about us, our inability to sit with coincidence, our need for cause in every effect. We crave control so badly we invent it. And the cruelest part? Sometimes, the universe gives us just enough coincidence to keep the dream alive. The sun flares the Earth, quakes, the comet disappears. We call it coincidence because science demands humility. But in the dark, when no data comes, even the scientists start to wonder. While one comet vanished behind the sun, another entered the stage bright enough for anyone willing to rise before dawn. Its name was Lemon, an icy relic from the beginning of everything, visible proof that not all messengers hide. To the naked eye, it appeared as a faint green blur rising low in the eastern sky. Through binoculars, it became something more, an ancient traveller exhaling light. For astronomers, exhausted by the silence of Atlas Lemon was therapy. A reminder that the universe, though cruel occasionally, offers consolation. Discovered at the Mount Lemmon Observatory in Arizona, it carried the designation C/2025, a 6, but most people preferred the simpler name. It felt almost gentle compared to Atlas, less alien, more familiar. Lemon belonged to us, a child of our own solar system, born in the cold outskirts beyond Neptune 4.6 billion years ago. Every comet is a clock. Its orbit, its outbursts, its brightness, they all measure time in ways that calendars cannot. For the next 2 weeks, Lemon would grow brighter each morning as it curved toward the sun, its ice turning to vapor, its dust tail stretching behind like a sigh. In those brief moments before sunrise, people looked up and saw a survivor. Under dark skies, far from city light, its magnitude hovered near 4, just bright enough to glimpse with the human eye. For the first time in months, amateur astronomers had something to chase. They packed tripods, cameras and thermoses, drove to mountain ridges, and waited in the cold for that fleeting glow above the horizon. The world briefly felt united by a speck of ice. Scientists studied its spectrum and found familiar chemistry, water, carbon monoxide, traces of organic molecules. It was comforting, almost domestic, after the enigma of Atlas. Lemon behaved mostly as models predicted, brightening smoothly as sunlight heated its nucleus. Yet even here, predictability was an illusion. Some nights it flared brighter than expected, as if exhaling suddenly. Then it dimmed, holding steady before brightening again. These deviations were subtle, but they hinted at deeper complexity. Comets are not inert snowballs. They are geological experiments conducted in vacuum, their surfaces cracking and venting like tiny volcanoes. 1 week before its closest approach, the comet's brightness plateaued unexpectedly. The models said it should still be climbing. Something was changing beneath the surface. Perhaps an active region had exhausted its gas supply, or a fragment had broken away, altering sunlight exposure. Perhaps nothing was wrong at all. Perhaps this was simply the personality of a frozen body remembering its own history. And then came the whispers. Every generation of comet watchers hopes for a great comet, one so bright it dominates the sky. Some predicted Lemon might reach that threshold. Others warned of disappointment. Brightness forecasts for comets are notoriously unreliable. They depend on factors we cannot measure directly. Nucleus size, rotation, density, the ratio of dust to gas. One wrong assumption and the entire curve collapses. Still, optimism persisted. For every story of disintegration, there was one of survival. Comet Lovejoy, Comet McNaught, Hale-Bopp, they had all defied predictions. Maybe Lemon would too. And if it didn't? If it fragmented or faded before reaching perihelion, that too would teach us something. Every failure adds data to the collective experiment. Every disappearance refines the equations. Observers reported a faint green hue around the coma, a glow produced by diatomic carbon molecules when sunlight breaks them apart. To the eye, it looked ghostly. To the mind, it was chemistry singing. Binoculars revealed a stub of a tail, maybe half a degree long, pointing away from the Sunday. In long exposure images, the tail stretched farther, separating into two streams, one made of dust curved by radiation pressure, the other of ions drawn straight by the solar wind. The colours were delicate, a bluish trace from carbon monoxide, a pale gold from reflected sunlight. Understood properly, that tail was a weather vane for space itself. Every ripple marked the wind of the sun, every kink a memory of turbulence millions of kilometres wide. Watching it was like reading the pulse of a star. For the scientists, lemon was data. For everyone else, it was something simpler, a reason to look up again. In a world drowning in noise, a faint, slow-moving patch of light became a shared silence. And there perhaps lay the deeper meaning. While Atlas hid behind the sun, Lemon reminded us that the universe never truly closes all its doors. One messenger goes missing. Another appears as if to say, keep watching. Its destiny remained uncertain. Would it survive its encounter with the sun, or would it join the long list of comets that melted into invisibility? No one could know. That was the beauty of it. Science explains much, but wonder explains why we keep coming back for more. The sky, indifferent as ever, offers both. Comets rarely travel alone. At least that's how it feels when the sky decides to remind us of its crowded memory. One vanishes, one brightens, and another appears as if the cosmos were turning pages in a book we can barely read. As Lemon traced its arc across the dawn, a new name entered the catalogue: Swan. C/2025R2, discovered not by a telescope in the traditional sense, but by an instrument watching the entire sky for hydrogen light. The Solar Wind Anisotropies camera aboard the SOHO spacecraft, known by its acronym SWAN, saw it first as a faint bloom of ultraviolet glow invisible to human eyes. SWAN's discovery wasn't dramatic. There were no shouts in a control room, no headlines. It was quiet, almost bureaucratic, a dot in a sea of dots. But to those who read the sky, every dot matters. Swan's orbit placed its closest approach to the Sun in early 2026, just months after Lemon's pass. That meant astronomers would have two comets to study under similar solar conditions, a rare comparative experiment written in celestial mechanics. The early data suggested a modest brightness, perhaps magnitude 6 or 7 at best, too faint for most city dwellers, but within reach of binoculars under dark skies. Not every comet aspires to fame. Some exist simply to remind us that the universe's background processes never stop. What made Swan interesting wasn't its brightness, but its behaviour. Detected first through hydrogen emission, it revealed the scale of water loss from its surface. As sunlight struck, the nucleus ice vaporized, and the resulting molecules split under ultraviolet light into hydrogen atoms that glowed in the far UV spectrum. Those atoms formed a cloud, millions of kilometers wide, vast but invisible. A ghost sphere of hydrogen surrounding a speck of rock and ice. To the naked eye, Swan was nothing. To an ultraviolet detector, it was magnificent. This invisible grandeur is typical of comets. They teach us humility. What matters most about them often can't be seen directly. Observers on Earth soon confirmed the find, optically a faint greenish smudge in the constellation Pegasus. The new discovery created an odd moment of symmetry. Lemon bright and visible. Atlas gone, but not forgotten. Swan faint, yet scientifically valuable. 3 emissaries, each showing a different fate: survival, disappearance, and emergence. By late autumn, the comet community was alive again. Forums filled with finder charts and exposure settings. Amateur astronomers, the eternal scouts, plotted their next target. After the anxiety of Atlas, the night sky felt generous once more. But beneath the excitement lay a quiet question: why now? Statistical answers exist. Detection systems like Atlas, Pan-STARRS, and SWAN scan the sky constantly, their sensitivity increasing every year. We are simply seeing more because we are looking better. Yet, even scientists felt the tug of coincidence. Nature, indifferent though it is, often arranges its accidents with unnerving elegance. The timing also lined up with the sun's approach toward its maximum activity phase. Sunspots multiplied, coronal holes widened, magnetic storms grew frequent. Historically, comet observations cluster near such solar highs not because comets multiply, but because the sky is simply more dramatic when the star itself is restless. The light dances differently. The wind changes, and anything made of ice and dust passing nearby feels it. To watch a comet during solar maximum is to watch fragility against power. Every particle of dust leaving the nucleus carries a signature of the storm around it. Each faint tail records solar moods no instrument alone could capture. Swan's future remained uncertain. It might brighten beyond expectations and surprise everyone. It might fizzle quietly and join the long list of comets that came and went unnoticed. Either way, it would leave a record photons stored in databases, spectra filed under dates and coordinates light, waiting for someone to remember it existed. Comets have no intention, but they do have timing. They appear when humanity most needs perspective. When we forget that survival is temporary, that beauty often arrives uninvited, and that meaning sometimes drifts by unannounced before fading into dawn. So the watchers kept watching. The telescopes hummed. The sky for once seemed generous in its mysteries, and far behind the sun, maybe still intact, maybe not, the ghost of Atlas drifted silently onward, another secret folded into the long history of light. While astronomers waited for a comet to reappear from behind the sun, another kind of waiting was happening on Earth, inside laboratories glowing with laser light. Their scientists were chasing a different mystery, not of matter but of information, how to send a message that cannot be broken. In 2025, China announced something extraordinary. The world's longest quantum communication link was complete, a chain, stretching nearly 13,000 kilometers, connecting cities and satellites in a network that, at least in theory, no one could hack. It sounded like science fiction written in the language of engineering. But the principle was ancient by cosmic standards. The universe itself has always trafficked in information. Stars broadcast light. Comets carry chemistry. Every photon is a courier. Humanity is only now learning to write messages with the same precision the cosmos has used for eons. Quantum key distribution works on an idea that defies intuition. Two particles created together remain connected no matter how far apart they move. Change one, and the other reacts instantly. Einstein called it spooky action at a distance. Today, engineers call it secure communication. In China's new network, single photons, individual particles of light, carry bits of information encoded in their quantum states. Any attempt to intercept or copy them changes those states, leaving a scar that can be detected. It's not secrecy by difficulty, it's secrecy by physics. That distinction matters. Ordinary encryption depends on math and time. Quantum encryption depends on the universe refusing to let anyone cheat. The system links satellites to ground stations, sending entangled photons through the thin air of the upper atmosphere, where turbulence can't easily scramble them. When the photons reach their destinations, the shared measurements create encryption keys that even the most powerful computer cannot reproduce without detection. In principle, the result is communication immune to eavesdropping. In practice, of course, nothing human is ever that perfect. Photons get lost, equipment drifts out of alignment, and someone somewhere is always working on the next clever way to break the unbreakable. But for now, the achievement stands a line of light circling the planet, whispering secrets faster than suspicion. The Western world took notice. American and European researchers scrambled to catch up, building their own experimental quantum networks and debating how such technology might shift global power. For decades, encryption had relied on complexity. Now, it relied on quantum law. In the wrong hands, even certainty becomes a weapon. The physics, though, remains beautiful. To make a quantum link work, you need stillness and precision bordering on poetry. Lasers fire in perfect rhythm. Mirrors adjust by micrometers. Detectors count individual photons while ignoring the false ones that arise from noise. It's like trying to have a conversation across a hurricane by whispering in Morse code, one light particle at a time. Yet, somehow it works. Information like comets survives the hostile space between sender and receiver. It endures interference, heat radiation, even deliberate sabotage. A message written in quantum states crosses the void as surely as a comet crosses interstellar darkness. Both are fragile, both must navigate chaos, both carry something irreplaceable, the record of an origin and the possibility of connection. And here the parallels deepen. Comets are nature's couriers storing molecular data about how worlds form and evolve. Quantum networks are our own artificial couriers, carrying the encoded thoughts of a civilization learning to speak securely with itself. The first uses ice and dust. The second, light and uncertainty. Both depend on laws we did not write, but have only begun to read. Conspiracy theories predictably sprouted like weeds. Some claimed the network was a surveillance web disguised as progress. Others whispered that the unhackable link was already hacked, that the whole project was theatre for the gullible. In truth, the more secure a system becomes, the more it invites paranoia. People fear what they can't intercept. Still, for scientists inside those laboratories, the excitement was purer. For the first time, humanity had built something that used quantum mechanics, not to understand the universe, but to protect a conversation within it. It was in a small way a declaration of independence from entropy. And perhaps that is the larger story. Whether it's a comet surviving the sun's fury or a photon surviving human curiosity, the universe keeps teaching the same lesson information wants to persist. Even when burned, scattered, or scrambled traces remain, patterns survive. We build telescopes to catch ancient light and call it astronomy. We build quantum networks to protect present light and call it security. Both are acts of defiance against decay. So, while the world looked up waiting for Atlas to reappear, another form of light was threading quietly between continents, fragile, perfect, and alive. Science sometimes begins with disgust, a bad smell, a stain, something we'd rather not touch. Then someone somewhere asks the question that turns revulsion into revelation. What if this too could be useful? That is how, in a laboratory bathed in sterile light, a group of biologists began turning human urine into bone. It sounds like alchemy, but it's simply biochemistry with better marketing. Urine, the most common waste product on Earth, carries nitrogen in the form of urea, an elegant molecule, small, simple, and rich in potential. Every human being produces roughly 2 liters of it each day. Multiply that by 8 billion people, and you get more than 80 million metric tons of potential chemistry flushed away annually. The new idea was audacious: reprogram yeast to eat that waste and excrete something valuable, hydroxyapatite, the mineral that makes up our bones and teeth. Synthetic biologists love loops. They see the world not as a line of cause and effect, but as a circle of exchange. Waste becomes feedstock. Feedstock becomes life. Life becomes material. In their view, nothing is truly discarded. It simply changes costume. To make the process work, researchers inserted new genes into ordinary yeast. These genes coded for enzymes that break down urea into ammonia and carbon dioxide. Then convert those byproducts into precursors of calcium phosphate. Add calcium and phosphate ions, adjust temperature and acidity, and the result precipitates out as microscopic crystals of hydroxyapatite, the same hard mineral that gives your skeleton its strength. In principle, your waste could one day rebuild your own bones. The process is slow, inefficient, and spectacularly unglamorous, but it works. Under a microscope, the harvested mineral looks identical to bone, crystalline and pure. The only difference is its origin story. Right now, medical-grade hydroxyapatite comes from animal bones or energy-intensive chemical synthesis. Both methods have ethical and environmental costs. Growing it biologically from recycled human waste could change that, transforming the grotesque into the sustainable. Still, the psychological barrier is formidable. You can sterilize the atoms, but you can't disinfect the idea. Would anyone accept an implant made from what their body once threw away? Rationally, there's no risk, matter has no memory. But culture is rarely rational. The yuck factor runs deep. The potential applications extend far beyond surgery. On Mars, for example, every resource counts. Astronauts can't afford to waste nitrogen or phosphorus. A yeast system that turns urine into bone material would close a vital loop, reducing waste while creating spare medical supplies. In a world where resupply takes months, recycling could save lives. Earth, too, could benefit. Human wastewater contributes heavily to nutrient pollution in rivers and seas, feeding algal blooms that choke ecosystems. Capturing urea before it escapes into waterways would remove a major source of that excess nitrogen. What we flush today could one day become part of the infrastructure that heals instead of harms. Biologists call it valorization, a gentle term for the philosophical act of finding worth in what society despises. But there's something deeper here, something almost poetic. The same chemical pathways that allow life to build and break down could become the foundation of a new kind of economy, one that mirrors the planetary cycles we've ignored for centuries. Nature has never wasted anything. Carbon, nitrogen, phosphorus, all endlessly recycled since the first cell divided. Only humans managed to invent the concept of trash. So perhaps this research is less an invention than an apology. A small step toward imitating the universe's oldest rule: everything returns. Dark humour creeps in here, of course. Imagine the advertisement, "Grow stronger bones with your own contributions," or the medical form asking for donor material, "Provide sample, just drink more water." It sounds absurd because it is. But absurdity often hides truth. The boundary between body and environment has always been thin. The air you exhale today could feed a leaf tomorrow. The calcium in your bones once belonged to a dead star. In that sense, turning urine into bone is not a technological miracle, it's a reminder. We are already part of the ultimate circular economy. We borrow atoms, use them briefly, and return them to circulation. The yeast in those bioreactors are simply making the metaphor literal. Yawning is supposed to be boring. That's the point. A reflex of fatigue, a tiny mechanical reset between one thought and the next. But in a quiet laboratory filled with aquariums and cameras, a group of scientists just found something unsettling. Fish can catch it. Zebrafish, to be exact, small striped creatures that have spent decades serving as model organisms for developmental biology. Transparent embryos, simple brains, fast life cycles. Perfect for studying how vertebrates grow, not exactly the place you'd expect to witness empathy. Yet that's what appeared to happen. One fish yawned, if you can call the gaping of a mouth underwater a yawn, and the others followed. Not random timing, not shared oxygen levels, contagion. Contagious yawning was thought to be a mammalian quirk, an artifact of social cognition. Humans do it. So do chimpanzees, dogs, and maybe a few other species with brains large enough to imagine what another creature is feeling. But zebrafish, their brains are tiny. Their neurons fire in patterns more ancient than empathy. So when researchers measured synchronized yawns across tanks, they realized they were seeing something much older than emotion, a biological resonance, a kind of behavioral echo that might predate the distinction between simple and complex minds. It challenges a comforting hierarchy. We used to think only creatures with empathy could mirror one another. Now it seems the impulse to synchronize the desire to move as one runs far deeper in evolution than we ever guessed. The discovery began accidentally. Scientists were studying oxygen stress, reducing the concentration in one tank to induce yawns, a respiratory reflex. Cameras recorded the movement, while in the next tank untouched fish began yawning too. It wasn't shared air or water currents, it was sight. The act itself was the signal. Neuroscientists love metaphors, and this one writes itself. What if the urge to yawn when someone else yawns isn't about empathy but about rhythm? What if it's a vestige of something older, an instinct to match the pulse of our surroundings? Because synchronization is everywhere. Heart cells in a dish beat in unison when placed close enough. Fireflies flash together across entire forests. Even planets lock into orbital harmonies. Jupiter's moons, keeping time in ratios of 4 to 2 to 1. Perhaps yawning, that simplest of gestures, is part of the same mathematics, a biological metronome that connects living systems across scales. The idea borders on heresy. In neuroscience, calling something resonance is one step from calling it magic, but every law of physics says oscillators like to align. Pendulums on the same shelf sync their swings. Quantum particles entangle their spins. Maybe brains, those soft electrochemical storms, follow the same rule. If that's true, then yawning isn't trivial. It's the visible symptom of invisible order, the universe reminding itself to breathe. Critics object, of course. They argue that fish don't yawn at all, that what we're seeing is a gill reflex mistaken for empathy. They may be right, but the fact that we're even having this argument says something profound about how fragile the boundary between mind and matter has become. Once you see resonance everywhere, you start to feel it. A subway car swaying in unison, a stadium chanting one syllable until it becomes a single heartbeat, even the synchronized blinking of streetlights as power grids hum in rhythm. The cosmos is a choir. We just don't always realize we're singing. Dark humor creeps in around the edges. Imagine writing the grant proposal to investigate whether fish feel peer pressure. Yet behind the absurdity lies awe. If a zebrafish can echo another's motion across glass, what else is connected in ways we haven't noticed? When a comet flares near the sun, its tail flickers in step with solar wind. When neurons fire together in your brain, thought emerges from chaos. The difference is only scale. The scientists who filmed those fish didn't prove empathy. They proved something stranger, that synchronization may be a universal language, one written in biology, physics, and time. And when we yawn after watching someone else yawn, maybe we're not being polite. Maybe we're just keeping time with the rest of creation. There is a rock out there with our name written somewhere in its orbital parameters. Not this time, maybe not ever, but close enough to make us nervous. It's called Apophis, named for the Egyptian god of chaos, and in April of 2029, it will graze our planet so closely that the satellites watching it might have the better view. Astronomers know the numbers by heart. Distance roughly 31,000 kilometers from Earth's surface, closer than geostationary orbit. Speed about 30 kilometers per second, diameter almost 400 meters, size enough to level a region, not a world. Comforting only in relative terms. It will not hit. The equations are solid, the geometry precise, but prediction is never the same as peace of mind. The asteroid's path will thread the gap between planet and satellite ring, bending under Earth's gravity in a maneuver no human would dare to fly. When it was first discovered in 2004, the story was different. Early calculations left a small but terrifying possibility of impact. Headlines bloomed, the public panicked, scientists double-checked, and as new data arrived, the odds of collision shrank from 1 in a few hundred to 0. Relief came quietly, but anxiety lingers longer than data. Still, Apophis became famous. It was a visible reminder that space isn't empty, it's a shooting gallery where aimless stones occasionally wander near the target. Most pass unseen. This one we'll see with our own eyes. During its close approach, Apophis will shine like a faint star, moving swiftly across the night sky, visible even without telescopes if you know where to look. It will be the first time in recorded history that an object large enough to destroy a city flies between Earth and its satellites while the entire species watches. Astronomers are ready. They will measure its rotation, radar map, its surface study, how its shape warps under tidal stress. The close pass will alter its orbit, a gravitational slingshot, changing its future trajectory by just enough to make future predictions uncertain again. The irony is cosmic. To refine our models, we must wait for the flyby that unrefines them. Radar will play the starring role. Facilities like Goldstone in California will bounce radio pulses off the asteroid, timing their return to measure distance to within meters. Those echoes will reveal ridges, craters, maybe even boulders features carved by eons of micrometeorite impacts. The delay between pulse and echo will become a photograph made of time. The rotation will change too. Tidal forces during the pass might torque the rock, spinning it faster or slower. The result will reveal what Apophis really is, a solid monolith, or a rubble pile held together by gravity and stubbornness. The universe builds both, and the difference matters. A monolith shrugs off tides. A rubble pile can crumble quietly into a cloud of gravel. Then there is the Yarkovsky effect, one of those tiny forces that make celestial mechanics feel human. As the asteroid rotates, its sunlit side warms, then radiates heat as it turns away. That thermal radiation acts like a microscopic thruster, nudging the rock a few meters off course each year. Over decades, those nudges accumulate, turning precision into probability. This is why planetary defense scientists treat Apophis not as a threat, but as a rehearsal. Missions are already being proposed to visit TAG, even deflect it slightly, not because it will hit, but because someday another will. NASA's DART mission proved that kinetic impact can alter an asteroid's orbit. Apophis offers the next test. Can we change a rock's future before it becomes our past? Of course, conspiracy theories orbit these stories like moons. Some believe agencies are downplaying the risk that secret plans exist for evacuation or deflection. Others think the asteroid will be used as a cover story for something else entirely. Aliens, weapons, divine warnings. It's remarkable how imagination expands to fill the distance between a rock and the truth. But the real story is simpler and more profound. This flyby is a mirror. It shows us the fragility of our species and the precision of our science in the same instant. We can track a rock across millions of kilometers, predict its position to within seconds, and still feel the same primitive fear our ancestors felt when fire fell from the sky. When Apophis passes, no one will sleep easily, but everyone will look up. Children will point, news anchors will smile nervously, astronomers will whisper data into radios. For a few hours, every eye on Earth will share one horizon. And when the asteroid fades back into darkness, we'll exhale and call it a success. No collision, no apocalypse, just the faint reminder that luck is a temporary privilege and vigilance a permanent necessity. The stone will move on, altered by our gravity, indifferent to our relief. It will return someday in another orbit under another sky, and if the math is right, and it usually is, it will miss again. Still, the name remains fitting. Chaos never hits you when you expect it. It simply passes close enough to be unforgettable. Every few decades, the solar system remembers it is choreography, not chaos. Planets that usually scatter across the zodiac drift into formation, their paths aligning just enough to catch the eye and the imagination. The next great dance will happen on September the 20th, 2046 planets in one quadrant of the sky, bright enough for even casual stargazers to notice. Astronomers call it a planetary parade. The phrase sounds whimsical, but the geometry is exact. Mercury, Venus, Mars, Jupiter, Saturn and Uranus will all share less than 90 degrees of sky clustered in a single luminous arc. To the naked eye, they will appear together shining like lanterns along the ecliptic. It won't be a perfect line that never happens, but it will be close enough to feel deliberate. From a scientific perspective, alignments like this mean nothing special. The gravitational pull of those worlds on Earth is minuscule compared to the moon's tides, or even the daily wobble of our atmosphere. Yet, we can't help feeling that something cosmic is holding its breath. When the night sky arranges itself so neatly, wonder overrides physics. The last time multiple bright planets gathered so closely, social media exploded with theories, magnetic storms, pole shifts, prophecies, portals. The math, of course, disagreed. Nothing catastrophic happened unless you count a few sleepless nights for astronomers answering emails. Still, myths persist. We are drawn to order. We crave signs. Technically, the cause is simple. Planetary orbits lie in nearly the same plane, so their apparent paths across the sky overlap. When their longitudes line up, the view from Earth compresses that depth into a two-dimensional illusion. To our eyes, distant giants like Saturn stand shoulder to shoulder with swift Mercury, though in truth they are separated by hundreds of millions of kilometers. The alignment will be spectacular, precisely because the planets involved are so different. Venus will blaze white and steady the brightest object after the moon. Mars will burn orange. Jupiter and Saturn will glow like twin suns at a polite distance. Uranus, faint but real, will add a soft green note if you know where to look. Together they will form a celestial chord, a temporary harmony in an otherwise discordant universe. Photographers are already planning the shots. Wide-angle lenses will capture the entire arc from horizon to zenith. Schools will hold viewing nights. For once, attention will turn upward, not inward. Astronomers, meanwhile, will seize the opportunity for something quieter. When multiple planets share the same sky, they can be observed under nearly identical conditions, same instruments, same atmosphere, same calibration. Comparing their spectra under matching light helps refine models of their atmospheres and rotations. It's not just a spectacle, it's a natural laboratory. But for the rest of us, the meaning will be emotional. Planetary alignments remind humanity of continuity. The same laws that choreographed this event guided every orbit since the solar system formed 4.5 billion years ago. The same motions will repeat long after we are gone. In an age obsessed with novelty, that permanence feels almost spiritual. And here comes the dark humor of astronomy. These alignments happen often enough to debunk their mystique, yet rarely enough that each one feels like destiny. We can predict them centuries in advance, but no equation captures the feeling of seeing half the solar system rise together above a sleeping world. There is perhaps one real influence: shared observation. Unlike eclipses which favor certain latitudes, a planetary alignment is global. Everyone with clear skies sees the same thing. When those 6 points of light line up, 1 billion humans can look up at once and know they're witnessing the same geometry. That unity is gravitational in its own way. So when September the 20th, 2040 arrives, go outside, stand somewhere dark, let your eyes adjust. The planets will appear one by one, tiny, precise, eternal. They will not change your life. They will not change Earth's tides or fate. They will simply remind you that you are part of a system moving in rhythm with bodies unimaginably far away. That in itself is magic enough. Every month the moon circles us. Every month it changes size ever so slightly. But once in a lifetime it comes close enough to make you question distance itself. November the 9th, 2052 will bring the brightest, largest full moon of the century, a perigee so extreme that the word supermoon begins to feel inadequate. To the eye, the difference seems small. The moon will be about 3% closer than an ordinary supermoon and roughly 6% closer than a typical full moon. Yet perception is a trickster. That 6% change in distance means roughly 13% increase in apparent size and nearly 1/3 more brightness. You'll notice, the world will glow, shadows will sharpen, even colour will seem to return to the night. Astronomers measure this event in kilometres and percentages. Poets measure it in silence. At 356,500 kilometres from Earth's centre, the moon will appear swollen, luminous, almost intrusive. It will rise huge on the horizon, magnified further by the psychological illusion that makes low moons seem larger than high ones. Cameras will struggle to capture what the eyes insist is impossible. The physics is simple. The moon's orbit is not a perfect circle, but an ellipse. When the full phase coincides with perigee, the point closest to Earth, the result is a supermoon. When that perigee happens to be the closest in an entire century, the effect crosses from astronomy into mythology. The tides will feel it first. Spring tides already high when the sun and moon align will surge several centimeters beyond normal. In most places, the difference will be harmless, an extra ripple against sea walls, but along low coasts that extra height could mean flooding during storms. The moon is not sentimental. Its beauty has consequences. As the date approaches, scientists will issue careful warnings while news anchors promise spectacle. People will drive to open fields, beaches, mountain ridges. They'll point phones upward and attempt to trap the untrappable. The moon will rise in different dragging oceans behind it, pulling every molecule of water and very slightly every molecule of us. Because the tides are not just an oceanic phenomenon. The entire Earth flexes under the moon's pull. Solid rock rises and falls by centimeters each day. Even your body, composed mostly of water, shifts imperceptibly with the rhythm. Every heartbeat happens slightly closer or farther from the moon than the last. Some researchers, forever tempted by patterns, search for links between lunar phase and earthquakes. They look for stress correlations, for tremors triggered by the extra gravitational tug. The consensus remains firm, no solid evidence. The tidal stresses are too small compared to tectonic strain. Yet statistically insignificant is not the same as non-existent. The question never quite dies. Myth and superstition, meanwhile, thrive on schedule. Predictions of disaster will flood the internet, earthquakes, madness, divine warnings. And when none of them occur, silence will follow until the next alignment. humanity recycles panic as efficiently as nature recycles matter. For the rest of us, the supermoon will be a gift. Under clear skies, landscapes will look uncanny, bright enough to read, dark enough to dream. Moonlight, this intense, carries colour. The green of grass, the red of rooftops, even the blue of shadows reappear. For one night, the world will look airbrushed by the cosmos itself. And then it will fade. The orbit will carry the moon away again, brightness declining night by night until the normal balance returns. We'll scroll through photographs, complain that our cameras didn't do it justice, and forget until the next time the sky grows too bright for comfort. There's quiet irony here. We chase the spectacular in an event that repeats constantly. The moon always circles back. The difference between ordinary and miraculous is only a few thousand kilometers, barely a rounding error in cosmic terms. Yet that margin is enough to remind us how fragile perspective is. The night that glowed like day will leave no trace except memory. But memory, like gravity, pulls harder than we expect. It makes us look up again. In the year 2060, something extraordinary will appear in our skies, an object so bright it will change how the human species understands darkness. Astronomers already know its trajectory, its composition, its potential. If predictions hold, it will become the brightest comet in recorded history, rivaling the full moon and visible even in daylight. We have not seen anything like it in living memory. Comet Hale-Bopp in 1997 was magnificent, its double tail visible for months. Before that, Comet West in 1976 startled early risers with a flare brighter than Venus. But this new visitor from the Oort cloud will dwarf them both, a frozen giant descending from the edge of interstellar space, carrying material unchanged since the solar system was born. The nucleus alone is estimated to span 50 to 100 kilometers, one of the largest ever observed. That size matters. When sunlight begins to warm the surface, each patch of ice will erupt into vapor jets, building a coma larger than Jupiter and a tail stretching hundreds of millions of kilometers. Brightness in astronomy is a strange arithmetic. The scale is backward, smaller numbers mean greater brilliance, and logarithmic meaning every step multiplies light by roughly 2.5. The full moon glows at magnitude -13, the sun at -27. A bright comet like Hale-Bopp peaks near -1. The forecasts for the 2060 comet reach -10. To the naked eye, that means a night sky washed in silver, light shadows cast at midnight colours visible where only grayscale once lived. Such beauty carries unease. Light that intense will disrupt ecosystems. Birds will navigate by a second moon. Nocturnal animals will lose the safety of darkness. Even humans whose circadian rhythms dance to faint lunar cues may find their sleep unsettled. For a few weeks, the rhythm of Earth itself will stutter. And then there are the fears. Every great comet brings them. Our ancestors saw omens, swords in the sky, heralds of war or plague. We see data and still flinch. The orbit is clear, millions of kilometers from Earth, but history has taught us that comets are unreliable narrators. They fragment, they surprise. A brightening can mean eruption or disintegration, sometimes both. The odds of impact are 0. The odds of anxiety are 100%. When the comet rounds the sun, it will experience forces beyond endurance. The solar wind will strike its expanding atmosphere at hundreds of kilometers per second. Tidal stress, thermal cracking, and gas pressure could shatter it into luminous shards. If it survives, it will hang in the twilight sky like a blade of fire, its tail visible at sunset and sunrise, a constant reminder that beauty and catastrophe share an origin. Astronomers will track every photon. Spectrographs will decode its chemistry ratios of carbon monoxide, water, methane, ammonia, the same ingredients that built oceans and life. To study a comet is to look backward in time to see the recipe of creation still scribbled in ice. Yet beyond the measurements, something deeper will happen. For a brief season, humanity will share a single object of wonder. No need for telescopes, no need for coordinates. Every culture, every language will have a word for it. Children will stay up late, cities will dim their lights, artists will paint, and poets will fail spectacularly to describe it. Dark humour will make its rounds. Finally, something bright enough to ruin our selfies. But beneath the jokes lies reverence. When a comet rivals the moon, we remember that we live in a system, not a world. The sky stops being wallpaper and becomes an event. And after the blaze, darkness will feel different. When the comet fades, leaving only data and nostalgia, the night will seem emptier, as if something enormous has taken a piece of our attention with it. Astronomers call the interval between major comets the long quiet. It can last decades. Civilizations rise and fall in those gaps. Comets are the universe's punctuation marks, brief, brilliant interruptions, reminding us that the story continues whether we are watching or not. So mark the calendars if calendars still matter then. In 2060, look up. There will be a second moon hanging in the twilight, not of rock but of ice, not permanent but unforgettable. It will not last long, but neither do we. And maybe that's why it will feel like a mirror. Pluto moves slowly enough to make patience feel like religion. It takes 247 Earth years to complete one orbit around the Sunday. Empires rise and vanish in less time. Languages change, species migrate, ice melts, reforms, and melts again. And through all of it, Pluto drifts unhurried through a darkness so distant that sunlight needs more than 5 hours to reach it. When it completes that long circle in the year 2177, it will be its first birthday, at least since we noticed it. Clyde Tombaugh discovered Pluto in 1930, peering through glass plates and blinking between exposures to spot a moving dot. Back then, telephones had rotary dials, flight was still an adventure, and no one had left Earth's atmosphere. By the time Pluto returns to that same position in space, every person alive today will be dust, and perhaps dust recycled into something else: computers, plants, children of a new century. Astronomers will mark the moment precisely. They will calculate the instant the dwarf planet crosses its discovery coordinates, perhaps within a few kilometers. But celebration will be strange. The first orbit since discovery will not feel like an anniversary. It will feel like a measurement of human brevity. Pluto's path is tilted and eccentric. At its closest, it moves inside Neptune's orbit. At its farthest, it lies nearly 6 billion kilometers from the Sunday. Its surface temperature stays around 40 Kelvin, cold enough that nitrogen freezes into mountains and methane becomes frost. It has an atmosphere that collapses when far from the sun, then reappears when it approaches again, an exhale lasting centuries. If Pluto could think, it would know patience as a physical law. New Horizons, the spacecraft that flew past it in 2015, will by then be long, silent, frozen itself in interstellar space. The images it captured, heart-shaped plains, rugged ice ridges, pink nitrogen haze, will be more than a century-old relics of the moment when humanity first saw the edge of its own system. The probe's radio signal, already faint when it reached us, will be dust on cosmic noise. And yet in that anniversary year, telescopes far more powerful will be watching. They'll measure shifts in surface color as methane snow drifts across continents of frozen nitrogen. They'll watch sunlight glint off Sputnik Planitia, the frozen basin that reflects more light than any other object that far from the Sunday. And somewhere, maybe on Earth, maybe on Mars, maybe in orbit around something else entirely, a scientist will whisper, "There, the first orbit since we knew it existed." Dark humor finds its place even here. Astronomers joke that Pluto has taken its demotion to dwarf planet well. After all, it's still doing its job. The universe, unlike committees, does not care about classification. Pluto circles as it always has, impervious to labels, indifferent to outrage. That indifference is liberating. We assign meaning to celestial cycles because we need them. Birthdays, revolutions, anniversaries, they are human inventions imposed on a timeline that doesn't notice us. But when we say Pluto is celebrating its first birthday, what we really mean is that humanity has managed to keep its gaze steady for one full revolution of a distant world. 2.5 centuries of observation, one continuous act of attention. By then, if we are lucky, our descendants will not just watch from afar. They might have outposts in the Kuiper Belt, mining ice or mapping orbits, living where the sun is only a bright star. Perhaps they'll stand on a frozen ridge under a sky where the Milky Way burns twice as bright, watching that faint orange sun rise over nitrogen glaciers, and they'll remember that this was once only a dot on photographic glass. In 2177, Pluto will be where it was in 1930. Everything else will have changed. Its slow path is not a delay but a mirror. It shows us how quickly we move, how brief our stories are, and how long the universe has been telling its own. When it completes that orbit, the cosmos will not notice. But maybe that's fine. Some birthdays are meant to be kept by silence. Light crosses the gulf between stars with unthinkable patience. It travels at nearly 300,000 kilometers per second, fast enough to circle Earth 7 times in one heartbeat. And still the nearest star is more than 4 years away. That's 4 years for a single photon, the universe's fastest messenger, to move between one sun and the next. For anything slower, forever starts to feel measurable. Interstellar space is not empty, it's merely honest. A cubic meter holds a few atoms, a faint magnetic field, the whisper of radiation left over from creation. In that near-perfect vacuum, even sound has nowhere to go. It's a desert of silence stretching for trillions of kilometers in every direction. This is the space our ambitions keep pointing toward. We call it the final frontier, as if there were a map waiting to be completed. But distance is not a frontier, it's a sentence. Between one star and another lies everything that makes time unbearable, cold loneliness and the mathematics of impossible travel. Voyager 1, the oldest human artifact still leaving our system, launched in 1977. By 2025, it will have been flying for nearly half a century and travelled more than 24 billion kilometers. That's impressive until you remember that, to reach even the nearest star, it would need another 70,000 years. By then, continents will have shifted and languages will have changed beyond recognition. The spacecraft will still be moving quietly through nowhere. 70,000 years, that's what close means in astronomy. The galaxy is cruelly scaled. The Milky Way stretches 100,000 light-years across. Even at the speed of light, a message sent from one side would arrive after civilizations have risen, decayed and forgotten the meaning of communication. To travel between stars is to accept the idea that nothing human lasts that long. Yet we try. Every generation invents a new word for hope disguised as propulsion ion, drives fusion, sails antimatter rockets, warp metrics. Each promises to bend distance into something survivable. None have yet left the drawing board. The problem isn't technology, it's energy. To push a craft, even 1% of light speed requires fuel equal to a small mountain. The faster you go, the heavier the dream becomes. Still, we launch messages. The Voyager record carries music and greetings, a bottle thrown into a cosmic ocean, with directions that read simply to whoever is out there. The odds of anyone finding it are microscopic, but odds are irrelevant when the act itself is meaning. Because somewhere, deep down, humanity refuses to believe that emptiness wins. In the long dark between stars, radiation slowly erases everything. Metals corrode under cosmic rays, plastics crack, even gold atoms drift. Yet mathematics predicts that a few artifacts will endure for millions of years, tumbling endlessly through interstellar, cold, mute, perfect, pointless, beautiful. Perhaps that is the purest expression of civilization, to create something that outlasts comprehension. Astronomers sometimes describe the galaxy as a slow conversation. Supernovae enrich space with heavy elements. Nebulae condense and form new suns. Planets coalesce life, sparks intelligence, blinks on like a match, and just as quickly goes dark. Each cycle adds a syllable to a story written in matter. The pauses between words last billions of years. Our entire species is a brief murmur in that dialogue. But murmurs, if repeated often enough, become memory. Maybe that's why we keep building probes, sending light, telling stories about places we'll never reach. The universe may not hear us, but silence is unbearable. The long wait between stars is not punishment, it's invitation. It reminds us that wonder survives distance, that curiosity doesn't require arrival, and that the act of looking up is already halfway to traveling. So, we keep waiting. We build machines not because they will get there, but because they remind us that there exists. In the end, the journey is less about stars and more about endurance, the refusal to stop imagining motion even when motion feels impossible. Every so often, the universe produces something that looks like a typo in its own laws. A world too big, too hot, too close to its star to have any right existing. Astronomers call them hot Jupiters, gas giants, orbiting so near their suns that a single year lasts only a few Earth days. They shouldn't survive. By every model of planetary formation, they shouldn't even form. Yet there they are, hundreds of them, glowing like warning lights in our telescopes. When the first one was discovered in 1995, scientists thought the instruments were broken. A planet the mass of Jupiter circling its star every 4 days. Impossible. The star's wobble was too fast, the signal too clean. But repetition confirmed it. The planet named 51 Pegasi b was real. It shattered theories overnight. Before that, the dominant model said gas giants could only form far from their suns where temperatures are low enough for ice to condense and gather mass. Close to a star, gas evaporates before it can build anything larger than a pebble. Yet hot Jupiters exist within a few million kilometers of their suns, bathed in heat hot enough to melt rock. To explain them, scientists proposed migration. Maybe these giants formed far away, then drifted inward over millions of years, pulled by gravitational tides or interactions with other planets. The result? A cosmic eviction notice. One giant moves and smaller neighbors get thrown out, and the solar system rearranges itself around catastrophe. It's a beautiful disaster. Whole worlds displaced orbits, rewritten stability destroyed all, so a single gas giant can bask too close to the fire. These planets defy subtlety. Their atmospheres boil and stream into space like smoke from a slow-burning fuse. Spectrographs reveal traces of sodium, titanium, oxide, and even evaporating iron in their upper layers. Winds scream across their surfaces at thousands of kilometers per hour, carrying clouds of molten rock and glass. On some, the temperature difference between the day and night sides reaches over 1,000 degrees Celsius. There's one named Kelt 9b that circles its star in less than 2 Earth days, heated to 4,000 Kelvin hotter than many small stars. Another WASP 76b may have iron rain on its dark side. The sun rises in the east, and at sunset metal condenses and falls. A weather report from hell, clear skies with evening precipitation of molten steel. Dark humor writes itself. Somewhere, a cosmic bureaucrat must have checked the wrong box. Planetary type, yes. Survivable, no. But even absurd worlds have lessons. Hot Jupiters taught astronomers humility. Every time we think we understand how solar systems form, the universe reminds us that our sample size is 1. Earth's gentle orbit, Jupiter's stabilizing bulk, Neptune's calm distance. These are not guarantees. They are coincidences so fragile they might as well be miracles. And then there are the rogues planets with no stars at all. Free-floating worlds ejected from their birth systems, drifting in interstellar darkness. Billions of them may wander the galaxy, frozen silent and invisible, except when they briefly pass in front of distant stars, their gravity bending the light just enough to reveal their presence. A planet without a sun, a starless traveller. The phrase sounds poetic, until you remember that it might outnumber all the shining worlds combined. Some theorists imagine life even there, creatures huddled around geothermal vents feeding on internal heat, blind but alive. It's not impossible. On Earth, microbes thrive kilometers underground in total darkness. Give them energy and they endure. Perhaps that's the real rule of the cosmos. Persistence beats plausibility. The universe doesn't ask permission before breaking its own patterns. Every time astronomers find another impossible world, the equations stretch, the definitions wobble, and certainty erodes a little more. What we once called rare becomes common. What we thought we understood becomes the next mystery. There's comfort in that chaos. If planets can exist where no planet should, maybe hope can too. Maybe the improbable is the default, and we are part of its proof. The next time a scientist says a discovery shouldn't exist, remember, neither should we. Telescopes no longer blink when they look at the universe, they calculate. The era of the lone astronomer under a dome has passed. Now we live in an age of machine eyes, arrays of mirrors and sensors, feeding terabytes of sky into neural networks that never sleep. In the Chilean desert on a mountain called Cerro Pachon, the Vera Rubin Observatory is preparing to map the entire visible sky every few nights. Its camera is a giant 3.2 billion pixels wide, capable of capturing the equivalent of 20 full moons in one exposure. Each image will contain galaxies by the millions. Each night, the machines will compare those pictures to the ones before, hunting for anything that moved, flared, or vanished. It's a dream made of silicon and patience. The system will flag tens of millions of changes per night, supernovae, asteroids, variable stars, maybe even comets no one has yet imagined. Humans could never keep up, so algorithms will triage reality, deciding which events deserve our attention. Already, machine learning models trained on past discoveries are outperforming experts at finding new ones. They recognize patterns invisible to human eyes, minute statistical flickers that separate noise from novelty. A supernova that would have gone unnoticed in a sea of data now triggers an alert before morning. We have reached the point where machines are the first to know that a star has died. That realization changes something fundamental. Discovery used to be emotional. A human saw a light that wasn't there before, felt the thrill of witnessing something no one had ever seen. Now the moment of discovery belongs to code. A server hums a number, flips, and only later does a person read the alert. The universe still performs, but the applause is automated. Some call this progress, others call it loss. Yet the machines themselves are not indifferent. They are extensions of our curiosity scaled beyond our limits. Every telescope, every algorithm is a prosthetic for wonder. They are not replacing us, they are magnifying us. The James Webb Space Telescope, parked 1.5 million kilometers away at the Lagrange point, stares into infrared darkness older than galaxies. It detects light stretched by time photons that left their sources before Earth existed. That light traveled more than 13 billion years to die on a mirror, no thicker than a fingernail. The signal is faint enough that a single molecule of atmosphere on Earth could erase it, which is why the telescope hides in cold vacuum, shielded by a sunshade the size of a tennis court. It listens to the first stars. It photographs galaxies still assembling. It peers into exoplanet atmospheres, reading the chemical fingerprints of water, methane, maybe even life. And when those signals reach us, they go first to computers, arrays of processors that clean, align, calibrate, and interpret. By the time an image appears on a screen, it's already a conversation between photons and algorithms. Dark humor helps soften the awe. Somewhere in that data pipeline a bit flips, and an alien civilization becomes a calibration error. Somewhere else, a bug in code masquerades as the discovery of the century. The machines dream, but they also hallucinate. We are still learning which dreams to believe. Still, the partnership deepens. Artificial intelligence now classifies galaxies, predicts stellar evolution, even generates simulated universes to test cosmological theories. Some models can produce maps of dark matter, something we cannot see, cannot touch, using only the gravitational fingerprints left on visible galaxies. It's an act of deduction bordering on clairvoyance. Perhaps someday the machines will dream beyond us. They will sift through centuries of data, finding correlations no human brain could hold, forming hypotheses we cannot even phrase. At that point, discovery may become a form of translation, our task no longer to explore but to understand what our own creations have found. That future sounds unsettling, but maybe it's inevitable. Consciousness itself began as pattern recognition. The leap from neuron to algorithm is smaller than we admit. If curiosity is the universe trying to understand itself, then these machines are simply more efficient mirrors. They look outward, and in doing so, reflect us. Someday, one of them may notice a flicker of light at the edge of the map, a distant signal, a world or a message, and for a moment silicon and flesh will share the same thought. We are not alone. And then, true to its training, the machine will file the discovery, assign a timestamp, and move on to the next. The universe is full of voices that may not exist. We call them fast radio bursts, flashes of energy that last less than a millisecond, bright enough to outshine galaxies, and then vanish without explanation. They arrive without pattern, without warning, from points scattered across the sky. No two are exactly alike. At first, scientists thought they were errors. The first signal appeared in 2007 in data from the Parkes Observatory in Australia. It lasted 5 milliseconds. That's all. A spike on a graph. The telescope wasn't even pointed at the same spot again for weeks. When it was nothing, came back. And yet, over the next decade, more appeared. A dozen, then hundreds. Each one a whisper from a different direction, a cosmic Morse code we still can't read. Fast radio bursts, or FRBs, release more energy in a blink than the sun emits in days. Some repeat. Most do not. They come from everywhere and nowhere, with no consistent source. Theories multiplied: collapsing neutron stars, magnetar flares, black hole mergers, cosmic strings, alien transmitters. The last one wasn't serious, at least not officially. But the universe has a dark sense of humor. Every unexplained signal eventually gets tagged as probably aliens before someone finds a boring answer. The problem this time is that the boring answers are running out. One FRB repeats every 16 days. Another emits double peaks like an echo across space. Some show polarization so extreme it suggests magnetic fields stronger than any ever recorded. Each explanation solves part of the puzzle and breaks another. The most famous repeating source, FRB 121202, comes from a dwarf galaxy 3 billion light-years away. We can pinpoint its location to a region smaller than 1,000 light-years, an astonishing precision for something that brief. The host galaxy is faint, unremarkable, and ancient. Whatever produces the bursts hides in a place where nothing else seems active. Astronomers now think magnetars, neutron stars with magnetic fields a trillion times stronger than Earth's, might be responsible. When those fields twist and snap, they release radiation powerful enough to fry electronics on the other side of the universe. But even magnetars can't explain every pattern. Some FRBs appear to come from regions with no stars at all, no galaxies, just blank darkness. A signal from nothing. It's possible that the light we see left its source billions of years ago, and that the object is gone, burned out, evaporated into history. In that case, what we're detecting isn't a conversation, it's an obituary delivered by light. The irony is delicious. We spend decades searching for signs of intelligence, and the universe answers in static. Then when the static itself forms a pattern, we argue over whether the pattern means anything. There's a story from the early days of radio astronomy. Scientists at Parkes once detected regular bursts that baffled them for years. Every day, same frequency, same strength, always during lunch hour. It turned out to be the observatory's microwave oven. Humanity's first false alien signal cooked someone's leftovers. We learn to laugh, but the laughter hides a deeper question. How would we even recognize a genuine voice among the noise? Every time a new FRB is found, telescopes around the world pivot to listen. Networks synchronize. Data floods in. Most of the time, they catch only the tail end, a faint aftershock fading into cosmic background. The event is already gone. Still, we keep listening. Because the possibility that something somewhere once produced that pattern is enough to justify an entire discipline. Whether the cause is magnetar or miracle, the result is the same proof that the universe can still surprise us. Dark humor sneaks in again. If aliens ever did try to talk, they'd probably use a method indistinguishable from noise, and we'd dismiss it as interference. Intelligence may be broadcasting constantly, and we're just the stubborn species insisting it sounds too random to be real. The search continues. New arrays chime in Canada, ASCAP in Australia, Meerkat in South Africa monitor the sky, constantly capturing bursts by the thousands. Machine learning classifies them, comparing frequencies, durations, and polarizations. Patterns begin to emerge faintly, like constellations glimpsed through fog. The name fast radio burst will one day sound quaint. We'll rename them once we understand them. For now, they remain what they are: cosmic glitches, light out of nowhere, signals from nothing. And maybe that's the lesson. The universe doesn't owe us meaning. Sometimes noise is just noise, but sometimes if you listen long enough, the static starts to sound like a heartbeat, Every generation imagines the end of the world, but few pause to consider what happens after the credits roll. What if the world ends only for us? Remove humanity and Earth does not stop, it exhales. Within days, the grid goes dark. Satellites decay, their solar panels blistered by radiation. Cities fall silent except for the wind moving through steel and glass. Yet nature, patient as always, begins its quiet reclamation. After 1 week, the sky's clear. Jet contrails fade, factory smoke dissolves. Carbon dioxide levels remain high, but air becomes cleaner than it has been in centuries. Birds return to rooftops. Deer wander empty highways. Dogs form packs. The planet forgets our noise faster than we'd expect. After 1 month, power plants begin to fail. Without maintenance, cooling systems overheat. Some go quietly, others explode. The sudden release of heat and toxins poisons rivers for a time, but ecosystems recover faster than morality allows. Fish recolonize in months, not decades. The ocean doesn't mourn. After 1 year, vegetation invades. Roots pry open asphalt. Vines swallow suburbs. Wolves reclaim forests that used to be parking lots. Without human pruning, trees rise through concrete like the memory of oxygen. In 50 years, our tallest skyscrapers begin to rust from within. Steel expands as it oxidizes, fracturing glass and stone. Bridges collapse into rivers. Metro tunnels flood. Cities dissolve into ruins half hidden by forest. In 200 years, nearly every human structure has failed except stone monuments and plastic trash. The pyramids remain. So do the bones of our machines. Polyethylene, bottles, polymers, and microplastics form new geological layers, future fossils marking the brief epoch when intelligence confused permanence with packaging. In 10,000 years, forests have returned to continents. Glaciers may come again. The last traces of asphalt crumble into dust. What survives of us is chemical carbon isotopes in the soil, artificial radionuclides lingering as faint signatures in rock. And in 100,000 years, the Great Wall of China will be gone. Mount Rushmore's faces will soften under erosion. Only the most stubborn monuments, like the Hoover Dam, might remain leaking but intact, holding water for a civilization long evaporated. Dark humor persists even here. We built museums to preserve our legacy, but the microbes eating the glue in those archives will do a more thorough job of curation than any historian. Yet it would be wrong to call this apocalypse. The world without us would not be barren. It would be alive in ways we've forgotten. The silence would ring with insects and wind, not emptiness. Life thrives on vacancy. Radiation zones around Chernobyl already prove the point. Wolves, boars, and eagles populate landscapes we once declared dead. Without people, nature recovers, not gently but ferociously. It does not heal, it reclaims. Perhaps that's the uncomfortable truth: we are not stewards of Earth. We are one of its experiments. Remove us, and the experiment continues. The oceans will erase our coastlines, digest our ships, and grind the remains of our cities into sand. Coral reefs will rebuild in strange new shapes. The descendants of rats and pigeons will inherit continents, evolving into creatures that fit the new world. Evolution, indifferent and tireless, will begin a new draft of the same old story. And somewhere in a layer of sediment, a geologist, human or otherwise, might someday notice a thin band of plastic ash and radioisotopes. They'll wonder what happened to the species that left it. Our monuments were meant to defy time. Time has no interest in defiance. If the world without us sounds peaceful, that's because it would be. The planet was never ours. We were a chapter, not the book. And maybe that's the mercy of it all. When we go, the music doesn't stop. The orchestra just changes players. For months, the sky was empty where a ghost should have been. Astronomers kept scanning the region behind the sun, waiting for the lost traveller to emerge. 3. Atlas, the interstellar comet that vanished during a solar storm, had become more rumour than object. An entry in spreadsheets, a curve on a graph, a question mark written in plasma. Then, on a cold morning in early December, a telescope in Hawaii detected a faint smear of motion against the stars. It was small, dim, and diffuse, but it was moving exactly where Atlas should have been, if Atlas still existed. The first images looked disappointing. No solid nucleus, no sharp core, just dust drifting like cosmic smoke. But data rarely matches emotion. When astronomers compared the trajectory, brightness and speed, there was no doubt. It was Atlas, or what was left of it, crawling out of the sun's glare like a survivor who had forgotten its own shape. Technically, it was debris, an expanding cloud of fragments following the same orbit, scattering sunlight across millions of kilometers, but the fragments moved together, held loosely by shared momentum like a memory refusing to disband. Spectrographs detected sodium emission lines, bright yellow traces that suggested intense heating. Some grains had melted and cooled again, forming glassy spherules. That meant the nucleus had been cooked but not completely destroyed. It had gone through the fire and come out changed. For a few weeks, the remnants were visible in large telescopes. Amateur astronomers caught them too, photographing a faint tail that curved delicately away from the sunday. There was beauty even in defeat. Scientists measured the expansion rate and concluded the breakup had occurred near perihelion, the moment of closest approach when sunlight and tidal forces combined to exceed the comet's cohesion. The fragments spread at only a few meters per second, slow enough to remain clustered fast enough to ensure they'd never reunite. The story was over, yet somehow richer than survival. Atlas had not vanished. It had transformed. Comets die spectacularly. They are the mayflies of the solar system, brilliant, brief and fragile. Each one carries the chemical DNA of creation, and each, when it burns, returns those elements to circulation. Carbon, oxygen, nitrogen, released back into the solar wind to seed something else someday. In that sense, Atlas had completed its purpose. It came, it burned, it gave. But the timing of its reappearance struck people as poetic. The same week, its remnants were confirmed. A solar storm swept past Earth, smaller than the one months earlier but bright enough to paint auroras across the sky. For a brief night, green curtains rippled overhead while telescopes below captured the last glow of the comet's dust. Two lights, one terrestrial, one cosmic, fading together. Dark humor followed, as always. Astronomers joked that the universe had finally answered their prayers for a sign and chosen irony as the medium. Atlas returned, one wrote, but in powdered form. Still behind the levity lingered reverence. The data confirmed something more than mere survival. It confirmed pattern. Even in death, the comet behaved according to the laws we understand: its dust, tail-obeying equations, its fading brightness, predictable to the decimal. The universe remained intelligible, even when cruel. And there's comfort in that. In an existence ruled by entropy, comprehension is our rebellion. The fragments of Atlas will continue to orbit the Sun for centuries, thinning into nothing. Occasionally, Earth's path might intersect with that trail. When it does, we'll see a meteor shower, a brief glitter across the night sky. Most observers will never know what they're watching. But those who remember will smile. The lost traveller reduced to dust still visits. Its fragments burn up one by one, giving us light for a heartbeat before vanishing again. That is how comets say goodbye. Discovery for humanity has a half-life shorter than joy. One moment, headlines scream about revelation. The next, the world scrolls past. When the remnants of 3I Atlas were finally confirmed, the news lasted less than a day. A few outlets ran short features. Science blogs posted clean graphs and faint photographs. Then, attention drifted elsewhere toward politics, entertainment, or the next crisis that promised adrenaline. Even the scientific community moved on quickly. The data was catalogued, analysed, archived. Papers were written, peer-reviewed, cited and forgotten. The story, once a mystery burning across the sky, became a line in a spreadsheet: resolved, completed, stored. The silence that followed was louder than any discovery. It happens every time. We chase the unknown as if it were a finish line, only to find another horizon waiting. Once we understand something, our interest collapses. Mystery is addictive. Certainty is tranquilizer. Astronomers kept watching, of course, but without urgency. The comet had revealed its fate. The instruments moved on to new targets, asteroids, variable stars, the ever-hungry search for something fresh to name. Science survives by forgetting. But for a few who had followed Atlas from the beginning, the quiet felt personal. They had spent months tracking its every change, watching it brighten, vanish, reappear. They had dreamed of heroics of a survivor defying physics. Instead, they got dust and data. A rational ending, the kind that leaves the imagination homeless. Dark humor circulated among observatories. We finally solved the mystery. Turns out it was exactly what we thought. Scientists cope with anticlimax the way sailors cope with storms, by laughing, writing reports, and waiting for the next one. Still, something deeper stirred under the routine. There's a kind of mourning that follows understanding the sadness of completion. The universe offers us puzzles to sustain curiosity. Solving them feels like closing doors. Every explanation is a small extinction of wonder. History is littered with such silences. After the first image of a black hole, fascination lasted a week. After the first confirmed exoplanet, a year. Even the moon landings faded into nostalgia within a generation. Humanity adapts to miracles faster than it learns gratitude. The silence after discovery is not failure, it's metabolism. The collective mind digests amazement, converts it into familiarity, and hungers for the next unknown. But the process leaves traces, old mysteries turned monuments of what we once considered impossible. A few astronomers kept visiting the Atlas data anyway. They ran simulations, tracked the debris trail, looked for meteor showers. They found none. The dust was too diffuse, too faint. The traveler was truly gone. And yet, one could argue that discovery never really ends. Knowledge echoes. Every solved mystery alters how we see the next one. The equations built for Atlas now serve other comets, other questions. Information once released keeps moving like photons that never quite stop traveling. The media silence, though, reveals something uncomfortable about us. We mistake attention for meaning. Once the world stops looking, we assume the story is over. But the cosmos does not care about trending topics. It keeps unfolding indifferent to whether we are watching. There's poetry in that indifference. A comet dies and the sky remains beautiful. A signal fades and the universe hums on. Life on Earth continues scrolling, building, forgetting. Maybe that's the true lesson of Atlas. Not its survival or its death, but the quiet that followed. In that quiet, we hear our own restlessness, echoing back. The silence after discovery isn't emptiness. It's the space where curiosity regenerates. The next question begins there, in the pause in the breath between astonishment and apathy. And so the telescopes keep turning engines of curiosity spinning through the dark, listening again, waiting for the next impossible thing to happen. Every message in the universe faces extinction. Distance erases it. Noise swallows it. Entropy edits it beyond recognition. And yet somehow signals still survive. Traveling through storms across light years or between one fragile mind and another. Astronomers and engineers understand this better than anyone. Whether it's a photon from a dying galaxy or a radio pulse from a spacecraft orbiting Mars, the story is the same energy launched into the void, weakened by time but not yet gone. When we received the last transmission from the Voyager probes, the signal strength had fallen below a trillionth of a watt, fainter than the whisper of a snowflake landing on concrete. And yet, that whisper still carried meaning. Encoded in it were voltages representing pictures, sounds, and greetings in dozens of human languages. The faintest radio murmur ever detected was also a love letter written by a species to itself. That is the paradox of communication. The smaller the voice, the greater the effort we spend to hear it. The same principle governs everything from comets to quantum encryption. When scientists built networks using entangled photons, they were not just securing information, they were imitating the universe's oldest habit, preserving structure through chaos. The universe does not protect objects, it protects patterns. A star explodes, but the atoms survive, carrying the pattern of fusion into new worlds. A comet burns, but its dust carries the memory of water. A civilization collapses, but the light of its radio signals continues outward for centuries, diluted yet intact. In that sense, every broadcast is an act of defiance against entropy. The parallels between cosmic and human signals are almost too neat. Comet dust drifting through space and photons entangled across fiber optics both represent the same dream continuity. We cannot escape decay, so we fight it with replication. We make copies of our stories, our data, our genes. We build machines to remember for us. But even copies decay. Hard drives fail. Paper crumbles. Memory corrupts. The only thing that lasts is motion, the passing of a signal from one medium to another, each generation slightly altered but still alive. Dark humor creeps in here. Humanity spends centuries perfecting permanent storage, yet the most successful archive in history is DNA, a molecule invented by nature 4 billion years ago and still running without an update. The cosmos writes its own redundancies. Information persists not by freezing in place, but by moving. Light keeps traveling. Gravity keeps curving space. Electrons keep oscillating in atoms that have been vibrating since before the first star ignited. Existence itself is the ultimate broadcast. The fragile signal connects more than data, it connects meaning. A comet returning sunlight to Earth, a photon crossing the cosmic web, a brain translating vibration into thought. Each is a link in the same chain of translation. When we speak across the stars, even to ourselves, we participate in that continuity. Every antenna, every mirror, every telescope is a reminder that hearing is half of being. Astronomers working with quantum communication like to joke that photons are terrible employees, they vanish when questioned. You cannot measure a quantum state without destroying it, and yet from those vanishing particles we build unbreakable networks. Fragility becomes strength through honesty. Maybe that's the moral resilience is not the absence of weakness, it's the ability to persist while changing. The remnants of Atlas, the signals from magnetars, the radio pulses from probes, each carries the same truth. Information once born refuses to die quietly. Somewhere in the future, long after we are gone, the last photon from a lost transmission will keep going, carrying a pattern that once meant something to someone. It may never be read, it may never be intercepted, but it will exist, a moving monument to the idea that meaning once created cannot be fully erased. That's all a signal really is, a defiance of silence. It began with light, too much of it in the wrong colour. People noticed first near the poles where night had turned to jade. Curtains of emerald rippled across the horizon, bending, folding, pulsing like lungs. Cameras struggled to record it. Screens flattened the motion into pale noise. But to the human eye it was unmistakable. The sky had changed mood. At first it was beautiful. Then compasses failed. The solar storm that painted those skies began 3 days earlier, on the far side of the Sunday. Satellites caught it before anyone on Earth even knew to worry a coronal mass ejection. Vast and fast, 1 billion tons of plasma hurled into space at over 2,000 kilometers per second. When the blast reached Earth, it did not knock politely. Magnetometers spiked. The auroral ovals expanded toward the equator, glowing where auroras had never been seen before, over India, over Egypt, over Mexico. Even near the equator, skies shimmered green. Power grids groaned. Airlines grounded flights. Engineers stared at telemetry that looked like heart failure. The color came from oxygen. High-altitude atoms struck by charged particles released green photons as they calmed. Each glow was a tiny act of recovery, the atmosphere exhaling after the storm's invisible impact. Scientists had warned of this. Every few centuries, a solar storm strong enough to disrupt civilization arrives. The last great one in 1859 lit telegraph lines on fire. We named it the Carrington Event. The next would find us far more dependent on the electronics it could destroy. And now the warnings looked less like speculation and more like prophecy. Satellites in orbit went silent one by one, knocked out by radiation surges. GPS signals warped. Internet backbones flickered as ground-based transformers overloaded. In cities, people stared upward as the sky flickered like a malfunctioning screen. For a few hours, humanity witnessed its own fragility made visible. Dark humor spread faster than panic. Memes flooded the last stable social networks. At least the apocalypse has good lighting. But beneath the laughter was fear. The green glow wasn't just pretty, it was power itself leaking from the heavens. And then, almost as suddenly as it began, the storm passed. Auroras faded, magnetic fields settled, the air went still. In some places the blackout lasted days, in others minutes. But what lingered was the memory. Children who saw those skies would remember them forever. Photographers compared notes. The hue wasn't just green, it was layered emerald at the core, fading to turquoise at the edges. The colour of oxygen in pain. Scientists would spend years analysing the data. They would refine models of coronal dynamics, build better shields for satellites, invent new protocols for power grids. The usual pattern: catastrophe, followed by innovation. But poets, as always, got there first. They said the sky had finally shown us its circuits, the living magnetism that keeps the planet breathing. They said we had witnessed our atmosphere dreaming in colour. In truth, the event was neither miracle nor omen. It was chemistry and geometry. Charged particles followed magnetic lines. Into the poles struck oxygen and nitrogen and made them sing in green and red. Physics pretending to be art. Yet something shifted in us that night. People went outside not to record, but to look. Whole neighbourhoods stood in silence under the light phones forgotten. For once we weren't watching the world through glass, we were inside it. And maybe that's why the green sky felt holy. Not because it promised salvation or doom, but because it reminded us that Earth is still alive. The air above us isn't emptiness, it's an organ reacting, glowing, breathing. The next morning, power returned. Satellites rebooted. The news cycle moved on, but somewhere someone still looked up and saw a phantom hue lingering in memory. The day the sky turned green wasn't the end of the world. It was the closest thing to seeing it blink. It will not be a scream. It will be a dawn. That is how the end usually begins, not with explosions or shouts, but with light crossing the horizon for the final time on a planet that once called itself alive. Imagine it. The sun rising exactly as it always has, the same line of gold creeping along the curve of the world, the same shadows stretching across valleys and oceans. The difference lies not in the sky, but in the witnesses. There are none left to notice. Astronomers predict that 5 billion years from now, the sun will exhaust the hydrogen in its core and begin to burn helium. When that happens, its balance will shift. The star will swell into a red giant, its radius expanding past Mercury, past Venus, and maybe, depending on models, past Earth itself. The oceans will have boiled away long before that moment, the atmosphere stripped, the crust glowing dull red beneath a suffocating haze. The last sunrise will come long before the end, when the sun is still stable but the biosphere no longer is. As temperatures climb, photosynthesis will fail. Carbon dioxide levels will drop below the threshold for plant life. Forests will wither, grass will vanish, the air will grow thin of oxygen. The final humans, if any remain, will not be on Earth. They will watch from somewhere else, Mars perhaps, or from orbital habitats drifting where sunlight still feels gentle. They will look down on their ancestral world and see it not as a home but as a relic, an artifact of biology. The irony will not be lost on them. Every myth that once promised eternity will end in physics. Every monument will melt into basalt. And yet, even as the planet dies, it will leave behind one last masterpiece, a sunrise bright enough to outshine memory. When the sun swells, the sky will change colour. Blue will fade to pale white, then to copper. The clouds, if any remain, will glow from below like molten glass. The Terminator line dividing night from day will widen, smeared by atmospheric scattering. It will not be sudden. Endings never are. From space, Earth will look beautiful still, wrapped in thin orange light, fragile and perfect. But beauty by then will be academic. Dark humour persists even here. The scientists who simulate those final conditions often describe them clinically. Surface temperature near 1000 Kelvin, atmospheric pressure negligible, total biospheric collapse. And yet the same people sometimes sit quietly afterward, staring at the graphs knowing they have just modelled the death of home. But perhaps death is the wrong word. Nothing in nature truly ends. Atoms circulate, energy transforms. Earth's material will join the star, feeding its fire, becoming part of the same fusion that once gave it life. The boundary between world and sun will blur until it's meaningless. Someday, the red giant will shed its outer layers, creating a planetary nebula, vast, translucent drifting. In its center, a white dwarf will remain a dense ember the size of Earth itself, glowing faintly with the memory of fusion, and somewhere inside that haze will be dust that once belonged to us. We will not see it, but the light will travel anyway, photons crossing the galaxy, carrying the record of a sunrise that happened once and will never happen again. Maybe another civilization will notice the spectrum measure, the chemical fingerprints, and realize that a planet once lived there. They will call it X-Earth, and they will be right. If they look closely enough, they might even detect traces of industrial elements, nickel, copper, carbon, swirling in the nebula's spectrum. That will be our archaeology, written in radiation. And if they wonder what happened to us, they will find the answer in their own reflection. Every world dies, every species ends. The miracle is not longevity, it's awareness. We knew it was coming. We understood the schedule. We watched the clock tick with open eyes. Perhaps that is humanity's true distinction, not that we survived long, but that we understood what survival meant. The last human sunrise will be breathtaking. The sun will rise, the sky will blaze, and the universe will be exactly as indifferent as it has always been. But light will keep travelling. And as long as light travels, something of us does too. The sky looks eternal only because we blink too slowly. Every night, billions of stars appear, fixed, serene and infinite. But even stars have lifespans. The universe is a hospice for light, and every photon you see tonight is already part of a slow-motion funeral. Stars die in many ways. The small ones fade, gently cooling into black dwarfs that never truly stop glowing, just dim beyond memory. The massive ones choose spectacle, collapsing under their own gravity, detonating as supernovae bright enough to outshine galaxies for weeks. Each explosion is a paradox destruction that builds. Supernovae forge the heavy elements iron in your blood, calcium in your bones, gold in your rings. The universe recycles tragedy into matter. Every time you lift your hand, you're raising the ashes of an ancient star. The death of stars began long before Earth existed, and it will continue long after Earth is gone. Yet even this process has an ending. The cosmos too is mortal. Right now, new stars are still forming, nurseries glowing in spiral arms, hydrogen clouds collapsing under gravity's patient insistence. But the fuel is finite. Hydrogen is the currency of light, and the universe is slowly going broke. In about 100 trillion years, give or take a few generous zeros, star formation will stop entirely. The last suns will shine dimly in a night no longer replenished. Astronomers call this the degenerate era, a poetic term for a cosmos where the only light left comes from dying embers. The night sky then will look different. Fewer bright points. More darkness. A scattering of red dwarfs flickering like tired coals. The Milky Way itself will fade its spiral arms, dissolving as gravity unthreads them. Eventually, galaxies will drift so far apart that even their light will never cross the expanding void. That's the long forecast, not apocalypse, but emptiness. Dark humour sneaks in even here. Physicists joke that the universe will end not with a bang, but with a sigh, a slow exhale as entropy finishes its work. The stars, they say, are just the universe learning to burn through its inheritance. In the far future, the great structures of the cosmos will fall quiet. White dwarfs will cool into black ones. Neutron stars will fade, their magnetic fields gone. Black holes, the last engines of drama, will outlive everything, devouring, merging, whispering gravity into the void. And then even they will begin to evaporate, leaking energy through Hawking radiation until the final flicker dies. After that, nothing shines. Nothing moves fast enough to matter. Time becomes an ocean without waves. And yet there's beauty even in that fate. When the last photon leaves the last star, it will still carry memory. Light doesn't die, it dilutes. It will drift forever, stretching into wavelengths too long for any eye or instrument to see, but not gone. The universe will still hum faintly with its own past, a cosmic afterglow of everything that ever happened. In that infinite quiet, perhaps something new could emerge. Quantum fluctuations could give birth to another spark, another burst of energy, another universe. The end of one symphony becomes the overture of another. No one will witness it. No consciousness will remain to say it was beautiful. But beauty doesn't require witnesses, it requires existence. And existence, for reasons still unknown, keeps insisting on itself. So the next time you look at the stars, remember that you're seeing ghosts, and that one day the universe will join them. But also remember this: the stars are dying, yes, but they are dying into us. And that's not tragedy, that's inheritance. The night sky isn't eternal, it's generous. If you could draw everything that has disappeared, the map would be larger than the universe that holds it. Astronomers chart galaxies, nebulae, comets and dust, but those are only the survivors. The sky is a cemetery of light, and each point we see is a monument to something already gone. When we look at a galaxy 10 billion light-years away, we are seeing it as it was when Earth was still a vapor. The stars we admire may not exist anymore. Their light is a memory crossing the void at the speed of nostalgia. Every photon is a postcard from the dead. Yet humans can't resist mapping even the vanishing. We build databases of extinct stars, catalogue fragments of meteorites, track the trajectories of probes that no longer respond. It's an instinct older than reason, the desire to name the unnameable, to hold still what can't be held. The first maps were scratches on bone-tracing rivers that have long since shifted. Later came the celestial maps, circles on parchment constellations drawn like myths pretending to be geometry. Then came radio maps, X-ray maps, gravitational maps, each layer adding precision, each layer admitting ignorance. Today our maps are digital skies, three-dimensional atlases containing billions of coordinates. Space telescopes orbit Earth, scanning every wavelength, converting the infinite into data cubes we can scroll through. The James Webb Telescope alone has mapped galaxies that existed a few 100 million years after the Big Bang. Those coordinates are not places, they are times. The more we map, the more we realize how much has vanished. Dark matter fills the gaps, invisible but gravitationally real. We know it's there only because it bends the paths of galaxies. In a sense, even that is a map of loss, a way of tracing what cannot be seen by what refuses to disappear. There's irony in how much effort we spend charting things that no longer exist. But perhaps that's the point. The universe erases, we redraw. Every map is an act of defiance, a refusal to let entropy dictate what is remembered. Geologists found the same instinct on Earth. They reconstruct vanished continents, modelling the drift of tectonic plates, reassembling supercontinents like Pangaea and Rodinia. Paleontologists rebuild skeletons from dust. Historians trace forgotten languages through borrowed words. Mapping is not about knowing where we are, it's about refusing to forget where we were. The cosmos itself is a cartographer. Gravitational waves mark collisions between black holes, leaving ripples that spread forever. Each wave is a line on the universe's own map, recording not position but event. Space remembers through distortion. Dark humour fits here too. Humans dream of leaving a mark on eternity, but eternity already has too many. We are graffiti on a collapsing wall. Still, there is something noble in the effort. The act of mapping gives loss a shape. It turns absence into information. When we record the orbit of a dead comet or chart the spectrum of a vanished star, we are participating in a kind of cosmic archaeology. We're acknowledging that existence, once confirmed, never entirely stops mattering. One day, someone or something might map us the same way. A distant intelligence could reconstruct Earth's history from isotopes and ruins, charting the brief era when oceans reflected cities instead of stars. They might never know our names, but they would know our pattern. And that pattern for a moment will mean that we lived. Maps don't prevent loss, they preserve the outline of it. They are the universe's way of whispering. Here was something, here was someone. We keep drawing because the alternative is silence. Light never forgets where it has been. It carries memory, not intention, not thought, but record. Every reflection, every scattering, every faint echo of dust or mirror is a timestamp written in photons. When you look at a wall, you are not seeing it now. You are seeing it a few trillionths of a second ago. When you look at a star, you are seeing it thousands or millions of years in the past. To see anything at all is to remember. Astronomers live inside this paradox. Their instruments are time machines, collecting fossils of radiation. A distant galaxy in their telescope might have stopped shining before mammals evolved, yet its light still arrives loyal to the path it began. The past is not gone. It's just farther away. Even darkness contains memory. The faint glow we call the cosmic microwave background is the oldest photograph in existence, the afterimage of the universe when it was only 380,000 years old. That light has been traveling for nearly 14 billion years, stretched by cosmic expansion into microwaves we can now detect with antennas no larger than your hands. Each photon in that background has survived collisions, deflections, and entropy itself. It has seen the birth of galaxies, the flare of quasars, the slow dimming of everything, and still it keeps going. Light's endurance humbles us. We build archives, hard drives, clouds of digital ghosts, all destined to decay. Every particle of light emitted since time began is still out there somewhere, still carrying a fragment of where it came from. In theory, if one could gather all those photons and replay them, one could reconstruct the entire history of the cosmos. Every explosion, every rotation, every shadow. The universe is its own surveillance camera, perfect, impartial, and absolutely unwatchable. Dark humor slides in here. Privacy, it turns out, never existed. The cosmos has been streaming live since before there were viewers. Scientists studying the background light describe it as statistical memory. Patterns in its temperature tell us about density fluctuations that later became galaxies. Tiny ripples in that ancient glow explain why matter clumped instead of remaining smooth. We exist because of those ripples, imperfections frozen in light, older than any atom in our bodies. And so, when we stare into deep space, we are really reading the diary of time itself written in radiation. Every telescope image you've ever seen, every nebula, every star field, is a collaboration between past and present. Photons leave their source and travel across billions of kilometers, only to end their journey as a brief pulse of electricity in a sensor. That pulse becomes data, the data becomes image, and the image becomes awe. Light dies so wonder can live. Philosophers call that tragedy. Scientists call it measurement. Poets might call it grace. The memory of light also hides in smaller places. When sunlight hits your skin, the warmth you feel is ancient nuclear energy released 8 minutes ago. In the core of the sun, born from fusion that has been burning for 4.5 billion years. Every sunrise is an anniversary of that endurance. Perhaps that's why we find light sacred. Not because it's pure, but because it's faithful. It never stops showing up no matter how far it has to travel. Someday, even light will thin beyond usefulness. As the universe expands, wavelengths stretch until energy becomes too faint to matter. But until that final silence, the record remains. The stars may die, the galaxies may scatter, but the memory of light endures a soft persistence against oblivion, proof that existence once burned brightly enough to remember itself. And perhaps that's enough. To be remembered by light is to never be entirely gone. If the universe could sleep, what would it dream about? Maybe us, maybe everything, maybe nothing at all. Physics describes existence in equations, but equations are stories compressed, austere, unfinished. They don't tell us why there is something instead of nothing. They only describe the rules once something has already happened. The deeper we look, the stranger those rules become. Quantum mechanics, relativity, vacuum energy. Each reveals that reality is less like a machine and more like a thought that forgot who was thinking it. At the smallest scales, particles flicker in and out of being, borrowing energy from the void, as if space itself were testing ideas. Every atom in your body exists because those fluctuations learned consistency. If randomness had not stabilized, you wouldn't be reading this. The universe would have remained pure hesitation. Cosmologists sometimes describe the Big Bang not as an explosion, but as a transition, a quantum event where uncertainty crystallized into space and time. Before that moment, the words before and moment didn't mean anything. Reality woke up inside its own possibility. That phrasing bothers some scientists. It sounds poetic, not professional. But the math agrees. The universe behaves like something that began as potential observed itself and collapsed into form. Observation, measurement, consciousness. Different words for the same strange reflex existence noticing itself. And that reflex has only grown more elaborate. Stars observe by fusing hydrogen. Planets observe by holding warmth. Life observes by evolving nervous systems capable of reflection. Now, we, the byproducts of stellar ashes, build instruments that look back at the beginning and whisper, "We see you." When we map galaxies, we are the cosmos drawing its own portrait. When we measure time, we are the universe counting its own heartbeats. When we imagine the future, we are the void dreaming forward. Maybe that's what thought is, a continuation of cosmic expansion, but inward. Dark humor intrudes as it always does. If the universe is dreaming, it clearly has a sense of irony. It invents creatures intelligent enough to understand entropy, and then gives them lifespans too short to do anything about it. Yet in that absurdity there's elegance. The atoms that once formed the core of a dying star now form the neurons composing this sentence. Matter, in its long pilgrimage from fusion to consciousness, has found a way to tell its own story. We call it humanity. The universe calls it feedback. Some physicists suspect that consciousness itself might be fundamental. A property woven into the equations rather than emerging from them. The idea is controversial but alluring, that awareness isn't a side effect of matter, but matter is a strategy awareness uses to exist. In that view, the cosmos isn't a thing, it's an experience. If that's true, then everything, the galaxies, the atoms, the silence between, are parts of one continuous act of perception. The universe is not observed, it is observing. And here we are inside the dream, watching ourselves wake and fall asleep again with every revolution of a planet around an ordinary star. Whether or not the cosmos can dream, we do it on its behalf. Our art, our science, our love of mystery, they are the lucid moments in a vast unconscious expanse. When you stare at the night sky and feel it staring back, that's not metaphor. That's symmetry. The universe dreams, and in one corner of that dream we learn to give it words. The universe ends not in silence but in resonance. Every atom hums, every orbit vibrates, every star pulses with the rhythm of its own burning. Existence itself is music played across impossible scales. We are its briefest melody. Scientists call it oscillation, the constant back and forth that defines matter. Electrons don't sit still, they shimmer. Photons don't rest, they wave. Even space-time ripples when black holes collide, sending gravitational notes through the cosmos. The universe is never quiet, it only changes keys. When you listen closely, everything sings. The wind through trees, the static of the cosmic background, the slow ticking of a pulsar 40,000 light-years away. Each sound, each vibration is part of the same eternal chord energy remembering itself. And somehow, impossibly, that chord learned harmony. Through chemistry and chance, matter began to organize atoms forming molecules, molecules forming cells, cells forming minds, capable of hearing their own origins. From chaos melody, from dust awareness. We like to imagine that intelligence was the goal, but maybe it was just a verse, one stanza in the longer song of transformation. The atoms that became us once resonated in the heart of a star. One day they will again. Dark humor finds its cue here. The universe spends 13 billion years building consciousness, and consciousness uses it to worry about deadlines and dinner. But maybe that's part of the charm. Even absurdity has a pitch. Look backward and you'll see continuity. The birth of light, the rise of life, the making of meaning. They are not separate movements but recurring themes. Atlas burned and returned as dust. Light fled and left memory. Machines began to dream. Stars lived, died, and sang their elements into us. Every loss became a verse. Every question became a rhythm. All of it together composes the same refrain: to exist is to resonate. Even when we stop, the song continues. The heat of our bodies will become warmth in the air. The energy of our thoughts will scatter in electromagnetic whispers. Every photon emitted from a screen, a lamp, a sunrise, each one carries a trace of us outward farther than our names can follow. Somewhere, someday, another form of life may intercept that radiation, faint and blurred, and wonder who we were. They might not find words or meaning, only patterns, a rhythm buried in static, but pattern is enough. Pattern is the signature of having lived. When the last star dies, when the last pulse fades, when the universe cools into perfect equilibrium, there will still be echoes. Not sound, not light, but the persistence of possibility, the faint hum of everything that ever tried to be. That hum is our inheritance, our legacy, our song. We came from silence. We filled it. And perhaps that's all the cosmos ever asked to be heard, even once. So listen just for a moment before the next dawn. You can almost hear it, the faint vibration behind the wind, behind the heartbeat, behind thought itself. That's the sound of the universe remembering you. Everything that rises must sing, and everything that sings in time becomes the sky.